Imagine we are studying a small fraction of the universe, what in physics we would be calling a system. Depending on how it interacts with its environment, the system can be open, if it changes matter and energy, closed, only energy, or independent, neither of them. The science that studies how systems exchange energy is called thermodynamics. Energy exchanges may alter the system's state, which will be reflected by the physical variables that compose them. These variables can be extensive if they inform us about the size or extension of the system we are studying, such as the volume or the mass contained, or alternatively intensive if they are intrinsic to the system, such as the pressure or the temperature. These variables are related with each other through different mathematical formulas that have been experimentally tested and checked. On the other hand, their theoretical justification relies on four premises that are called the thermodynamic laws. Let's start with them. The third law. It tells us that if a system V is in thermal equilibrium with a system A and a system C, then A and C are also in equilibrium. And what is the indicator of this thermal equilibrium? Equal temperature. As easy as that. The first law, it says that energy is conserved in any isolated system. It can be created or destroyed. In other words, energy is finite but inexhaustible. Does this mean that energy can be recycled over and over forever? Unfortunately, no. Think about two systems with different temperatures. The thermal energy is expected to flow in one particular direction, and once the equilibrium is reached, this transfer energy will not be reusable. And this direction is very related with what we call as entropy. Now we are prepared to understand the importance of the second law, which says that total entropy never decreases. Yes, okay, but seriously, what is entropy? Let's put the next example. Imagine you are a teenager and your mother texts you that for the first day in your life, your room is tidy. With only that message, you might already have a very precise idea on how the different elements of your room are located. In contrast, if she texts complaining how untidy it is, you might have a hard time to visualize the particular disposition of each thing in the room. Chaos can exist in many different ways. Well, the truth is that in thermodynamics, the one that informs us about the situation is what we call as the macro state of our system, which, as already mentioned, is simply defined by the different thermodynamic variables that we can measure. But in the same way the text of your mother can be related with different situations, one macro state can have many different possible molecule and energy dispositions associated, what we call as microstates. So, statistically speaking, entropy is just the number of microstates associated with a macrostate. For that reason, we say that entropy may not decrease, because independently on which microstate we start, it is more likely to jump to a macrostate with more microstates associated than with one with a lower number. But hold your horses before stopping the video and start using the second law to justify how disorderly your room is. Notice that for this law we have used the word total. Local entropy can decrease sometimes in non-isolated systems. The important thing is that the universal entropy never decreases. And now the most obvious question that comes to our mind: how can we reduce entropy? The most simple way is by extracting thermal energy. In other words, reducing the temperature of the system. With this action, we force the molecules to acquire more strict dispositions. This is exactly the process that we perform when we make ice by freezing liquid water. But how far can we go? This is in fact answered by the third law: null temperature is unreachable. Hypothetically, when a system is at the absolute zero temperature, 0 Kelvin, their molecules have no motion. Thus, there is one unique possible microstate and the entropy is literally zero. Unfortunately, even if the chemists have done their best, it is impossible to extract all the thermal energy of a system. It will require infinite steps to do it. So please, do not try it at home. And with that final advice, we have already explained the thermodynamic laws. In the next videos, we're going to talk about how living systems manage to increase their entropy and more topics related with non-classical thermodynamics. Hope you have enjoyed it, and thank you for being here listening.